new topic now. So we've gone from talking about composition of functions, and now we're going to talk about a very special type of functions which have will have a special property which comes to composition. And these are one-to-one functions. And we say a function f is one-to-one if for any two different inputs in the domain, they must correspond to two different outputs in the range. Okay. So basically, if x1 and x2 are two numbers that are different, then they must go to different outputs. F of x1 is not equal to f of x2. Now, another way of thinking about this, if a function is one-to-one and f of x1 equals f of x2, then x1 equals x2. So basically, different inputs mean different outputs. That's the way to remember that for a one-to-one function. So look at some examples. If we have a map or a relationship or between the sets 1, 2, 3 and the set A, B, C, D, this first illustration that's not a function at all because the input 1 has two different outputs, so it's not a function. This second illustration, this is a function. Every input has exactly one output, but 1 and 2 have the same output, so therefore it's not one-to-one. And then here we have the outputs of 1, 2, and 3 are all distinct, so this would be a one-to-one function. So basically, nothing for it to be one-to-one. None of the outputs can be hit more than once. Now, when your function can be graphed, that is, if the domain and range, or the inputs and outputs, are real numbers, then there's a nice way to check it. If you just look at the graph, and we say that we have this analog to the vertical line test, which is the horizontal line test, which says f is one-to-one if every horizontal line intersects the graph of f at most once. It's the horizontal line, not the vertical line. The vertical line test tells you if something is a function. The horizontal line test tells you if it's one-to-one. And so, for example, here, the graph of f here, every horizontal line crosses it at most once. Okay, there are some horizontal lines that don't intersect it at all. That's fine, but there's no horizontal line that intersects it more than once. So this would be one-to-one. Here, this curve, we can see that there are lots of horizontal lines which will intersect it more than once. So this is not one-to-one. And the reason why for that is, let's say if we take these two, if we have 2 points of intersection, we have 2 points with the same y-coordinate but different x-coordinate. So let's say if this was like -2 and let's say this was 3, we would see that g of -2 is equal to g of 3. Okay, but of course -2 is not equal to 3, right? So as soon as we have 2 points of intersection, we know that it can't be one-to-one. So in particular, constant functions are never one-to-one. Obviously, with constant functions, all the inputs are the same. Non-constant linear functions, these are the graphs of those are just lines which are not horizontal. So obviously every horizontal line is going to intersect this exactly once. So these non-constant linear functions will always be one-to-one. Quadratic functions are never one-to-one because we know that their graphs are parabolas, so they don't pass the horizontal line test. And then we can see that there are some functions like x cubed, 1 over x. We look at their graphs and we can see that they pass the horizontal line test. Also, we can also see that prove this algebraically. For example, if 1 over x1 equals 1 over x2, then this obviously means that x1 equals x2, right? So that means that so 1 over x is one-to-one. X squared and x to the fourth are not one-to-one functions, and the reason why for this is, well, besides looking at the graph, we can see that f of -1, in this case, f of -1 would be -1 squared, which is equal to 1, which is equal to f of 1. Okay, so yeah, well, here we have two different inputs, but the same output. Okay, same thing with x to the fourth, or x to any even number. None of those will be one-to-one functions. And we can also see that the graph of those will look like this anyway. So they won't pass the horizontal line test. Okay. All right, so you think about this and say, all right, so what? Why do we care about this? Okay, well, we do this because the one-to-one functions will have another nice property. They're going to be invertible in a certain sense. So we want to talk about inverses of functions. And to do that, we need to go back to composition. So we say if f is a function, and we suppose that there is another function g such that f composed with g of x is equal to x, and g composed with f of x is equal to x. That is, f of g of x equals x for all x in the domain of g, and g of f of x equals x for all x in the domain of f. Then we say that g is the inverse function of f, and we use the notation f raised to the -1 to denote g. So basically you have, now in general, of course, we said that f circle g and g circle f are different, but in this case, if they're the same and they're both equal to x, then they're inverses of each other. So when you compose a function in its inverse, you always get x. The most important thing to keep in mind here is that the inverse function is not equal to 1 over f of x. Okay, I know it's a little strange because we like to, when we raise a number to -1, that's the same thing as taking its reciprocal. But this is an inverse with respect to composition, not multiplication. So that can trip some people up, but we want to keep that in mind. Okay, as an example, we can see that x plus 3 and x minus 3 are inverses of each other, because if we compose them, we get f of x minus 3, and so it's x minus 3 plus 3, and we get x. And if we compose them the other direction, let's try this. Okay. F inverse of x plus 3, this is x plus 3 minus 3, and that's x as well. Okay. So when you compose them in either direction, you get x. Same thing with x cubed and cube root of x. Basically, that's true because if we compose them one way, we get the cube root of x cubed. Okay, the cube root of x by definition is the number. If you cube it, you get x. Well, we're cubing it, so we get x. And similarly, if we take the cube root of x cubed, that's also going to be x, because there's only one number which can be the cube root of something. So those are inverses. And then, for example, 3, if we have 7x plus 4 and x minus 4 over 7, these will, those are inverses. If we plug this into here, we get 7 times x minus 4 over 7 plus 4. We compute this, that it's the 7's cancel, and we get x minus 4 plus 4, and that's equal to x. We could do it in the other direction. Okay, the 4's will cancel, and we get 7x over 7, which is x. Okay, so when we compose them in either direction, we see we get x. So these are inverses of each other, and of course you can see that this is clearly not equal to 1 over 7x plus 4. Okay, so now we will show you later on in the next video a way to compute these inverses if they exist. But first we want to say, well, why do we know, can we know that they exist, and what are the properties of inverse functions, which is what we're going to look at in the next video.